7 lesson 1. So we're doing solving first degree trig equations. So first degree just means exponent of 1. And then we're going to do solving second degree, which means exponent of 2. Okay? And what's going to be interesting about the second lesson, which we'll get into, is that you can factor stuff that are in sine and cosine. They can come in kind of like a quadratic form, kind of. Okay? So you kind of think about it in that way. But anyway, so this unit, we're going to solve algebraically and graphically for first and second degree trigonal equations expressed in degrees and with radians. We have a restricted domain and an unrestricted domain, which we use a general solution. The general solution is that idea that once you get the answer, you keep adding 2 pi to it, right? Because continuously we'll land on that same answer. So the idea that we'll do that for the period. Prove trig identities using reciprocal identities, so that's what we're doing later, not today. So in review, let's just look at these real quick. So it says, use algebraic procedure to solve the following equations of the given domain. Sine of x is -1/2. We're solving for x. Okay? So what you need to ask yourself is, what this is actually asking is, what location is sine -1/2? And you should feel good about this right now because -1/2 is on the unit circle. That's a common value for us. Okay? So this is kind of how you're going to go through this. You're going to say, okay, sine's negative where? Quadrants 3 and quadrants 4. So I know I'm down at the bottom because sine's y. Okay? Second thing to do is, what's the reference angle of when sine is 1/2? Well, with sine being 1/2, that's the one's closest to the x-axis, where the y is the shorter piece. So these reference angles are pi over 6 for a reference angle. You don't necessarily have to have that if you know what pi over 6 is here and pi over 6 is here. But the point is, it's the 30-degree cut. Okay? So pi over 6, right here, that means our answers of where sine is -1/2 is what? 7 pi over 6, 11 pi over 6 is the answers. Because 7 pi over 6 just past 1, 11 pi over 6 just before 2. That's your 2 cuts for sine, which you get -1/2. That's your answers. Okay? So again, if you want to ask yourself the question, we're finding when sine is -1/2. Sine is -1/2 at these locations. Why do I know I'm in radians? Because it gave me a 0 to 2 pi for my values, which I'm looking for. So we're not in degrees. Okay? Questions? You confused, Ty? What's wrong? Okay. Yeah, this is not written very good here. 7 pi over 6 and 11 pi over 6. Yeah, the bar was missing, so thank you.
And then the bottom one as well?
The bottom one, 11 pi over 6.
Oh, I thought it was 1 over.
Okay? So again, go through, where are my answers going to be? Where is sine 1/2? We need a -1/2, get in those quadrants. That's the process. Okay, let's look at this one. So this one's a little different because you're going to see we're going to solve for x. So secant x is 5/3. Well, 5/3 isn't on our unit circle. So that means we're not going to have an even 30 cut. That's okay. We can still do this. However, secant goes with what? Cosine. So we don't have a secant button to solve, so we're going to write this as secant x is 5/3. We're going to write as cosine x is 3/5. Now again, this isn't on the unit circle, and they also gave this to me. My restrictions are in degrees, so I'm solving for degrees now. So that's your indicator 1. My calculator should be in degree mode. And then this is where we're going to go ahead and go. Cos inverse of 3 over 5 will get me the degree measure for a reference angle. Okay? Is everybody okay so far? Okay, what do we get for the reference angle there? 53. Cool. So 53 is the angle. Now you ask yourself, we have cosine of 3/5. Is that positive? Yes. So 53 is a solution. We want, because we're talking about cosine, we want this answer of 53 and this answer of 53. So we want 53 and 360 minus 53. That gets me the other one. Okay? So your other answer is 307. 53 and 307. Any questions?
So if it's negative, like that one's get times both for negative.
Correct. Yeah, so you're always going to have a pair, right? Yeah. Okay, it's a good point. You're always going to have a pair, unless your restrictions only let you have one of them. Like if I said your restrictions are 0 to pi, then you only get one, right? Okay. Questions? Okay. All right. Let's keep on going here. Okay, so we're doing two types of solutions today. We're doing the actual solution, which we just did, where there are exact locations, and then we're going to do general solution where there's no restrictions. The general solution is that simple thing of once you find an answer, so we just had 11 pi over 6, right? If I wanted the general solution of that with no restrictions, we know that answer happens every 2 pi. And so we just do the 2 pi n thing, where n's going to be a positive integer. Okay? And so that will just tell you the possible solutions for the continuous curve. Okay? That's called the general solution. Okay? And so you take, and then the 7 pi over 6, you do the same thing. 7 pi over 6 is also plus 2 pi n. Okay, and that would be NEI. It can't be fractions. It can't be fractions. So let's see if you can figure this part out. We don't actually do an example of this, but you need to understand this. It's 2 pi because why? Full circle, that's my normal period, right? But what if my period changed? Like what? Yeah, if your period changed to 4 pi, then it would be every 4 pi. So this is it's not 2 pi every time, it's the period every time. Okay? So right now our period stayed 2 pi, which is fine. But if your period changes, then your general solution changes. Okay? Which makes sense because it's happening more often or happening less often. Okay? All right. We'll get to that here. So consider the graph here. We're going to look at these graphically in our calculators now. So and I have it in here for you. So sine x equals negative 1/2. So if we want to look at this in our calculator and we want to find the intercepts, we want one side to be 0. So what they did is they went ahead and added the 1/2 over. So looking at sine x plus 1/2 in the calculator. They said use this window, 0, 2 pi, pi over 6. They did 0, 2 pi because that's my restrictions. Negative 2 and 2 just have a good window, even though we know that's going to go 1/2 is going to be the highest, right? Because the max of sine is 1 plus 1/2, so 1/2 is the highest it's going to go. Okay, and so in y1 we put what I told you, and we're going to find the values in which it crosses the x-axis. We're doing the 0 method here because we set it equal to 0. Okay, so looking at the calculator, this is what you should have. I'll go through what you should have. Here's your y equals sine of x plus 1/2. Okay. And then we're going to look at the window. Okay, I put in there, I know they're decimals now, but I put in there 2 pi. So 6.828 is 2 pi. You can put 2 pi. Calculator probably changed decimal. Okay, and then my scale, I put pi over 6, like they said. So that's what pi over 6 is a decimal. Okay, so if you're not hearing me right here, I'll put it in there again. 2 second pi. See, same thing. And then second pi divided by 6. Same thing. Okay, so go to your graph. Here's your graph. We are trying to find the 2 zeros here and here. So again, 0. If you forgot to do 0, the 0 is second trace number 2. I go left of the 0. I'm already left of the first 0. Hit enter. Go right of the 0. Hit 0. Go left. Enter. 3.651914. Okay. So what we were going to do is that you're going to want to take that number and you want to, that's a radian value with pi already multiplied in. Let me say that again. That's a radian value with pi already multiplied in. So there's that thing where you want to divide the pi out and see what that fraction is that's with pi if you want to write it with radians. Okay, so 3.651914. You should be able to put that in. Let me see if it lets me. 3.665194. Let's see if I can remember. Yeah, you can just do x. I know. Do you want so you can just do x. You can just do x like she said. It knows that you're x right now. Don't you have to do graph x? Let's look here. Yeah. Yep. So you can just hit x. Do you hit enter? Yeah, you hit enter, right? Yeah. So it puts the value there for you from the calculator. Yeah. I wasn't sure if you guys knew that or not, so I wasn't sure to tell you. But yeah, thanks.
How did you know that?
Okay, so because the x comes from your graph that you just did. So there it is. So the point is you can divide pi. Okay, and then we want to find what that fraction is. So you hit math, fraction, 7 over 6. So my radian measure is 7 pi over 6. Because the pi is just hanging out, right? We took the pi out to see what the fraction was, and so the pi is still on that. So our actual answer here that we're going to go back to, 7 pi over 6. So that first location, this right here, the first location, that right there, whoa, that right there, yeah, you can take the graph and put it places, it's kind of cool. 7 pi over 6 is the first location. Just write that down on the line in the workbook, okay? I'm going to do the second 0 as well, okay? Second trace, let's go and do this again one more time. So we move over here, get to the other side where the other 0 is, enter. Oh, slow down, slow down. Enter. Okay, 5.795865. So then again, second quit. X equals, divide the pi. What's this fraction? 11 pi over 6. So 7 pi over 6 and 11 pi over 6 are the two solutions for that, which is funny because we just did that, right? You guys expected that. Okay? We just did that problem to start the class. So you should have right there 7 pi over 6, 11 pi over 6. Okay, this curve looks like this, goes up to here. Okay, so these two spots here is what we just got. Okay, use the following graphic method. Okay, so now what we're going to do is we're going to change they changed the window. Okay, so they changed the window on us to -2 pi to 4 pi. So we're looking at a wider range. So we're going to have more answers. Okay, however, what we just did is still within there. Okay, what we did is just still within there. We're not going to go through and find all these zeros. Okay, I'm going to save you that time. We know that 7 pi over 6 was a solution and 11 pi over 6 was a solution, right? And then we extended from 0 to 2 pi. We extended out another 2 pi and back another 2 pi. So we're picking up 2 more answers. So let me explain that one more time. We just did 0 to 2 pi, right? And now we're going to 4 pi and to -2 pi. So in here, we had 2 answers. 1, 2, 1, 2. We're going to have 2 more, because we have 2 more sections. Okay? So how you can figure that out is what I'm explaining to you, the general solution, is this answer of 7 pi over 6 we got. I'm going to add 2 pi to that. I'm going to get that one. And then I'm going to minus 2 pi to it. I'm going to get that one. Okay? Well, because every turn the same thing keeps happening. So in the regular 2 pi turn, we got 2. So then every 2 pi turn after that, it's always going to have 2 in it. Does that make sense? Okay? So we can simply do 7 pi over 6 plus 2 pi. So that's going to be 19 pi over 6. How did I get that? 12 over 6 is 2, right? 12 plus 7. What's that? Times what by 2? I don't think so. You add 2 pi, you subtract 2 pi. Okay, so 2 pi is 12 over 6 as a fraction, right? Why did I go 6? I'm in 6th here. So you can see 7 plus 12 is 19. So 19 pi over 6 is this guy. Add 12 this one, 23 pi over 6 is that guy. Makes sense, right? What is 4 pi in terms of 6? It's 24 over 6, right? So we're right before the 4 pi. So it kind of makes sense. They're kind of the same spot. Now we also go the other way, so I'll write these this way. If I go 7 pi minus 12, I get negative 5 pi over 6. 11 minus 12, I get negative pi over 6. Okay, again, that kind of makes sense because 7 pi over 6 is almost 2. So if I minus 2 pi, I'm just right before the start again, right? So that didn't go very far away from 0. So that's your 6 solutions. Okay, so notice the solution forms 2 sets of answers which differ by 2 pi. So what it's saying is, what I just kind of told you guys, is that the negative 5 pi over 6, the 7 pi over 6, and the 19 pi over 6 are all related. They're all the same position on the unit circle, okay, or on the rotation. I should say rotation. And then 11 pi over 6 was with the negative pi over 6, 11 pi over 6, and 23 pi over 6. Those are all the same location on the curve for y. So think about it this way, okay, if you're struggling understanding, these 3 values, at all 3 of these locations, they have the same output. Okay, the same y value, the same height. Okay, same thing here. They're the same, like obviously they're not the same x, you're putting in a different radian, but we know that if you keep putting in circles, it'll keep coming back. 2 pi, full rotation. All right, any questions? All right. Okay, so if the domain is changed to negative 4 pi to 6 pi, so we widen out 2 more each direction. Okay, write 2 more solutions for each set. Okay, so we widened out 2 more. So again, I'll kind of draw this one more time. So we started with 0 to 2 pi, and then we went from there to 4 pi to negative 2 pi, and now we're going to negative 4 pi to 6 pi. So we started with 1 section, then we went to 3 sections, and now we're at 5 sections. So we're going to have essentially 10 answers. We already have 6 of them. We're going to find 4 new ones, right? So I'm going to minus 2 pi. Let's do the top one first. So the top one was negative 5 pi over 6 was here, right? So I'm going to minus another 12 pi to that. So this is negative 17 pi over 6. And I'm going to come over here. In the 4 pi section, it was 19 pi over 6. I'm going to add another 12 to that. So in this section, it's 31 pi over 6. Again, if you're, why am I doing 12? I'm doing 12 over 6. 12 over 6 is 2. I'm just doing common denominator. That's why we keep doing 12. So if our cut was a cut of 4, what would I keep adding? Not 16. 8. 8 over 4. I keep adding 8 to all my 4s because 8 over 4 is 2, right? We're adding common denominators of 2. Okay, so if it was 3, I'd be adding 6. 6 thirds plus 6 thirds plus 6 thirds. 8 fourths plus 8 fourths plus 8 fourths. We're doing 12 6 plus 12 6 plus 12 6. Right, because we keep adding 2, because that's the 2 is the constant repeat, right? And this is kind of tedious in a way. Like, to me, these are all the same values. They're just making sure you know you could find on a different domain. So, but anyways, that's all the new ones. So these 2 are the ones I just wanted. We just got the 2 for the smaller one. So the other one was negative pi over 6 was here for the other one. So then minus 12 to that, that's negative 13 pi over 6. Okay. Then the other direction, this one over here was 23 pi over 6. And so add 12 to that, it's 35 pi over 6. So your two new ones for that part is this one. So you have 1, 2, 3, 4. We gained 4 more solutions by extending it 2 sections. Okay? And this is what I was telling you when we started this. Use the ideas above to write the general solution to the equation. So we don't have to keep doing this tediously. You can go ahead and say general solution is, so you can take the x equals 7 pi over 6, that first solution we got, and you can say plus 2 pi n. Okay? And then n, again, can be the EI. So that means that n can be a plus or minus number. So that means we can go either direction. But they have to be whole numbers. This is 7. So 7 pi over 6 plus 2 pi n. The other solution for that same question, because we had 2 sets, is 11 pi over 6 plus 2 pi n, also NEI. So those are the same. Again, that's how you write general. Okay? You write general and there's no limits. So if you don't have a domain restriction, then you have to write it in general because there's, you know the sine and cosine curves are continuous. They keep going. Come on, ask some questions. Some of you guys look like you're swimming.
So will you always have 2?
Pretty much, unless your restrictions make you only have 1. Like if it tell me I had it between 0 and pi and it was cosine.
But then you wouldn't have a general.
Right, if you have restrictions, you won't have general. So yeah, so in terms of general, you should have 2. Yeah. Okay. All right. Okay, and that's because everywhere in the unit circle is mirrored, right? Everywhere, every positive, negative is mirrored. Okay, the solution to the equation of sine of x to negative 1/2 in part B may also be obtained by using the intersection of 2 graphs. So you could, on the intersection feature, guys, you could do sine and then put the 1/2 in and do the intersection feature. Remember, both those options work. You guys should know that from Math 10 even. You guys do intersection versus zeros, so that's fine. Okay, let's look at this next one here. So, term the following procedure to find the general solution. Use a graph calculator to solve the equation where domain is one period of the graph of function. Use the intersect method or zero method. Okay, determine the general solution by adding or subtracting multiples of the period to the graph of solutions in 1. Okay, so here we go. Let's go ahead and do intersect this time. If you guys are okay with that. Well, this one's already equal to 0. What do you guys want to do? Want to try intersection? You want to do 0? You can do what you want then. I'll do intersect this time since I did 0 last time. To do intersect, you want cos x to equal 0.75. This goes in y1, this goes in y2, if you're going to do intersect. Okay, I'm just going to do the intersect this time. Okay, when you do that, your graph, so they put graphs to do both types. So if you do the 0 type, it's going to look, it says it's going to look something like this. That's what it look like if you do the 0 type. If you do the intersect, which we're doing right now, it's going to look more like this. Along those lines, and we're trying to find these 2 spots. Okay, so I'm going to lose these pictures in a second, so get down what you need, but if you're working on your calculator already, I'm going to join you. I'm going to do it on the calculator here in about 2 seconds. 1, 2, okay. Here we go. So let's go to y. Y equals, we'll clear this one. We're doing cos x in the first one. We're doing 0.75 in the second one. Let's see, window. My window should be okay. Okay, my window is good. Okay, so second trace. Intersect is faster on the calculator. You don't have to do left bound, right bound. You just have to do, make sure you're on the curve. I'm on the curve, enter, enter, enter. It's going to go to the left one there. So 0.7227. Okay. So this case, 0.72, you can go ahead and try to divide pi out and do that with radians, but it's not going to be a fraction, and that's okay. They're not all perfect radian cuts, so be okay with that. So if that's the case, just accept that this is the best it can be, and you just do plus 2 pi into it. So you just put point. No, you don't have to. Is what I'm saying. We divide by pi to get to fraction. So let's go and do it. That's fine. So let's go second quit. So if I go x, I'm going to keep crediting Leah. Thanks, Leah. Okay, if I do x, I divide by pi, I hit enter, and then I go math, and I hit fraction. It has nothing for me. So that means it's not an even cut, and that's okay. So you're going to take this answer here, and you're just going to put plus 2 pi into it. That's all you have to do. So, and then it says here, it says nearest hundredth, right? And that kind of gives it away to you. It's not going to be a nice number. So nearest hundredth is just going to be 0.72. So you're going to go on the workbook here. You're going to put, the first solution is going to be x equals 0.72 plus 2 pi n, NEI. Okay, I think you guys are good with using intersects. I'm going to go and just put the second answer up here for time. X equals 5.56 is the second one. And you're going to put plus 2 pi n. And then NEI again. NEI means that we can only have positive, negative integers for n, which means positive, negative whole numbers. That just makes your 2 pi stay whole. And that also means I can go left or right. Okay? All right, any questions on that? Okay. We'll finish this up here for this lesson. And we'll hit 2. Yes, of course. Of course. Okay, so solve the equation where domain is 1 period of the graph of the function. Okay, and the general solution can be determined by adding, subtracting multiples of the period and the solutions in 1. So once you solve for 1 period, you can always add 2 pi n or subtract 2 pi n for your period if that's the period. So use an algebraic procedure to find the solution of this one. Okay, you guys look at that. You should see the root 3 over 2 is coming. Okay, so you should feel like a little bit comfortable with that. Okay, so we're solving for this. It's going to be add the root 3, divide the 2. So we want to know, when is cos x a positive root 3 over 2? And so I was talking to a couple of you guys when you guys were in here early. If you know where this is at in the unit circle, your life's so much easier. Because what I say to myself is, where is cosine x the longer piece? That's how I read that. Where is cosine x the longer piece? Cosine's x. It's the one we already dealt with, isn't it? It's the 30 cuts. These cuts right here, cosine is root 3 over 2. Because it's the longer piece compared to y, right? Right, there's only going to be 2 spots, correct, but all those spots are root 3 over 2. They just change the positive, negative. So we want positive, so we want these 2. Okay, good. So that means we know we're in quadrant 1 and 4. Okay, we know our reference angle is 30, or wait, do they have this in radians? Oh, they want radians. So our reference angle in radians is pi over 6. So our 2 answers are x equals pi over 6 plus 2 pi n. X equals 7 pi over 6 plus 2 pi n. And then n, e, I. That's your general solution answer. 11 pi over 6, 11 pi over 6. Yeah, sorry. Thank you. 11 pi over 6. I don't know why I was thinking 7. 11. Almost 2, just past 1. Say that again. 2 pi n. No, good question. Okay, so he's asking, can you just minus it to get here? These are only pi over, these are only 90 degrees apart. Yeah, they're not, since they're the cosine, they're the same spot. I know what you're thinking. That's why we have to have 2 answers, because they operate in different locations. Okay, In some cases, the different parts of a general solution can be combined together in one. Determine the general solution in radians of the equation. So where is sine 0? So where is sine 0? Thinking about your unit circle. Sine is 0 at 0, pi, and 2 pi. Right? Start, halfway, finish. Those are spots where sine is 0. So the general solution, you can kind of see, though, this is what they're talking about. I could say 0 plus 2 pi, and I could say 2 pi plus 2 pi, and that's the same thing, right? But then also, notice, look at this pattern. 0, 1, 2. So actually, I simply could write what? Pi n. Every pi, sine is 0. Every pi, sine is 0. 1 pi, 2 pi, 3 pi, 4 pi, 5, like all of them. It's going to be 0 for sine. So you can pi n is NEI. So that's what they're talking about. You can combine the solution here. Would you be wrong if you wrote on a written and you wrote it out? No. Okay, no. But you could combine that to one simple one. Okay, and then cosine at 0. Pi over 2 and 3 pi over 2. So simply this one happens pi over 2 plus pi n. Happens every pi starting at pi over 2. Right? 1/2, 1.5, 2.5, 3.5. All those spots will be the same location. This time we have to add pi n because this one landed on pi. So we can just say pi n, but this one starts at pi over 2. So like in terms of where we're at, this is when cosine is 0. So it happens here, 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 here every time. And so like that's pi, that's a pi. So every time you add pi to this number, it's going to land back on that spot. So I guess to answer your question, Sydney, every time, every rotation of pi, cosine is 0 from pi over 2. Okay, good. All right, last little piece here for this one. Solve a restricted domain. Okay, use the following procedure to solve a trig equation on a restricted domain. Determine the period of the trig function. Solve the equation when it's between 0 and the period. Add or subtract multiples of the period that we need to get the restricted domain. So for this one, solve the following equation for specified domain. I see root 2 over 2's. What kind of cuts are those? 45's, good. So I mean, you kind of start to see these patterns come out where you kind of know what to expect. So I'm going to add root 2 over 2. Nope, but it should be positive. Okay, so, and I'll divide the 2. So sine x will end up being root 2 over 2, right? Now, they want degrees here, okay? And they're making you operate from 360 to 720. So they're just shifting you up. But I know I want root 2 over 2, and you need to, this is what like I really, really stress. You should be able to do this easily. Here and here are the ones I want. Sine is positive. I want the 45 cut here and the 45 cut here. This is 45. This is 135. But obviously, those aren't in what I want. So what am I going to do? Add 360 to both of them. Good job. Add 360. So my answers are 405 and what is that? 360, 495. That's it. Cotangent. Between 0 and negative pi. So that's a smaller, right? They only, with the 0 and negative pi, what are we talking about? We're talking about right here. 0 to negative pi, that's where they're wanting the answer for cotangent. So if we solve this, we're going to get negative, we're going to get cotan x equals negative 1 over root 3. Okay, yeah, and if we rationalize, we're going to get cotan x equals negative root 3 over 3. Oh, yeah, you could. Sure. Yeah. So for cotan x, so Aiden saw the head of the game, which is good. So actually, you're right, Aiden. I should have done that. So we guess we don't have to rationalize here because we are in cotangent. We prefer to look at tangent. So what Aiden's saying is that then just flip this to negative root 3. I think that might be what you said, Cash. Okay, so negative root 3, yeah, that's right. It's good too. You could do either way because tangent and cotangent just means you're either doing x over y or y over x, and you don't have to flip to tangent to do it because we're not going to calculate here. Tan at negative root 3 is on the units, like on our normal spots. What we need to know is if it's tan is negative, where am I? I have to be here because tan's positive in the third quadrant, right? So now we have to figure out, okay, well, if it's root 3 for tan, what's on top? Because that means it's a comparison. Here's the hints, guys. Where do root 3's come about? Root 3's come about at which cuts? 30, 60. So I know I'm talking about 30, 60s. We know that tan is y over x. So I want my root 3 to be on top. Because root 3 comes from root 3 over 2 or 1 over 2. Because remember, the 2's cancel. You get root 3 on top. So I'm looking for when y is root 3 over 2 is what I'm trying to get at. So where is y root 3 over 2 in the fourth quadrant? It's the 60 cut. It's this one. So what is that one? And we're in radians. So do your counting, right? So 11 pi over 6. So remember, this is, it's a third cut, right? So 11 pi over 6. What's the third cut here? 5 pi over 3? No, it's 5 pi over 3. Yeah, it's 5 pi over 3 because remember, 5 pi over 3 is what in terms of 6? It's 10 pi over 6. Remember? 10, 11, 12. So it's 5 pi over 3. Is that the answer? No. Why not? Is that between 0 and negative pi? We went back a third, right? So you just go, actually, you say negative pi over 3. We went back a third. We're going backwards. It's negative. 0 to negative pi. We went back a third. That's pi over 3 to get there, right? Okay, so you have to ask yourself, okay, if you don't like that, then what you could do, you know we have 5 pi over 3. We can subtract 2 pi to it if you want. What's 2 in terms of thirds? 6 over 3. What's 5 minus 6? Negative 1/3, right? So you can still do that too. But the point is, guys, is we're going this direction. So we can't put 5 pi over 3 as an answer because that's not in this domain. So we're just putting back pi over 3. Back pi over 3. Okay. Show you one more time here. Here's our location. We are going this direction. So what is this distance? That's a negative pi over 3.
How did you get the 2?
How did I know the y was root 3 over 2? When you simplify the fractions for tangent, when it's just root 3, that means the root 3 over 2 was on top. Is that what you mean? So I just know that when I simplify this fraction, we're doing our y over x's. That keeps the root 3 on top, and this means root 3 is on top because it's on top of the fraction. So that's the giveaway that y is the root 3 over 2. Yep, and that's how I got that. Okay, good. All right, stop there.